Hello, this is Lila Culbertson, and for my flow, I have chosen the Jeffery-Hamel Flow. It is two-dimensional, so the flow characteristics are only described by changes in velocity along two perpendicular planes. It is incompressible, so the fluid density remains constant throughout the flow, and it's a laminar flow, so the flow is smooth with no significant mixing. The Jeffery-Hamel flow describes the steady two-dimensional flow of a viscous fluid between two planes that meet at an angle. I chose to study this flow because it has relevance to fluid dynamics. There are applications in engineering, such as diffusers with the diverging flow, and it gives us insight into flow behavior. So studying the Jeffery-Hamel flow gives insights into the impact of channel geometry, Reynolds number, and boundary conditions on flow patterns, which are crucial for real-world applications like aerodynamic design. These are the analytical studies I found. The first study considers the flow of an incompressible viscous fluid due to a source or sink at the intersection of two rigid, non-parallel plane walls. The study presents the effects of Reynolds number and angle on the velocity profile in diverging and converging channels. VPM converges rapidly, requiring only 8 iterations of convergence. This method's results are compared with existing solutions, showing that VPM provides better accuracy with less computational effort. The OHAM, which does not depend on small parameters, has been recently applied to solve nonlinear equations in engineering problems. The study aims to solve a nonlinear Diffie-Q governing JH flow using OHAM, comparing the results with those obtained from the fourth order Runge-Kutta or RK numerical method. Plots and tables demonstrate the reliability and simplicity of OHAM. Lastly, various methods, including numerical calculations and semi-exact analytical techniques, are employed to solve these nonlinear equations. Among the semi-exact methods, the ADM is notable for not requiring linearization or discretization and has been successfully applied to solve various fluid dynamic problems. The study compares ADM solutions with numerical results obtained via the fourth order RK method. For high Reynolds numbers in divergent channels, flow separation is observed. The ADM method provides results closely matching those from boundary layer theory and slender channel theory. These are the experimental studies I found. I found that some of these articles cover multiple categories. As an example, I already talked about the first study, but it would also be considered an experimental study because we are varying parameters. In this case, the effects of Reynolds number and angle on the velocity profile in diverging and converging channels. For the second study, know that receptivity means to the process that leads to the laminar turbulent transition, where external disturbances excite instabilities in the fluid system, followed by linear amplification through the entrainment process. The growth of disturbances depends on the intensity and frequency of the external disturbances. The study focuses on the transition of the flow near critical Reynolds numbers. A state space model using linearized perturbed Navier-Stokes equations is formulating, including wall normal vorticity and velocity. The system's response to external forcing frequencies is evaluated. JH flows have a single resonant peak, indicating better stability compared to plain Poiseuille flow. Avoiding these frequencies can prevent early transition. The last study for experimental studies addresses how flow control aims to delay the transition process, reducing drag and flow-induced noise. While instabilities in plane channel flows have been extensively studied, the control of instabilities in converging and diverging JH flows have not been addressed. This study numerically investigates the optimal growth of disturbances in Jeffery-Hamel flow at various Reynolds numbers and converging and diverging angles. These are the numerical studies I found. The last study is the only new one on this slide in which stability of the flow of viscous fluid in a divergent straight wall channel is tackled by a finite difference method applied to the equation of the disturbance stream function. Regarding the boundary conditions for pressure and velocity components, I have made the following table. So we're going to look at this and let the velocity field be in polar coordinates. So we have the radial velocity and angular velocity at the no-slip boundary conditions at the channel walls. This enforces that the fluid sticks to the channel walls consistent with the viscous nature of the flow. For the symmetry axis, we have the following, which ensures that the flow remains symmetric about the center line of the channel. For the inlet condition, we have the following, in which for a prescribed inlet, capital V can be specified based on the desired flow rate or velocity profile, so constant or parabolic, for example. At the outlet condition, we have the following. For the boundary conditions for pressure, at the no flux condition for the channel walls, we have the following, which ensures no tangential pressure variation along the walls. For the symmetry axis, this maintains the symmetry of the pressure field. And for the inlet and outlet condition, the flow is driven by a pressure gradient in the radial direction. Key quantities to compute and display to provide meaningful insight into Jeffery-Hamel include the following. So we have the radial velocity profile. This is a function of the angular position at different radial distances. So we're plotting the radial velocity at selected numbers of the radial distances. Next, we have the angular velocity profile. The angular velocity as a function of theta showing the secondary flow behavior if present. So this would be the angular velocity plotted at different radial positions. Should be 0 for Jeffery-Hamel flow if pure radial symmetry is maintained. Next, we have the pressure field. This would be the pressure variations along the radial direction and angular direction. So this would be a contour plot of the pressure field. And some key features would be the linear pressure drop along the radial direction and the symmetry about theta equals 0 typically. Next, we have the skin friction coefficient. This is the dimensionless wall shear stress. We would do a variation of the skin friction coefficient plotted with Reynolds number or angular width, which is represented by 2 alpha. Note that a higher skin friction in narrower channels or at higher Reynolds numbers. Next, we have the pressure drop. This would be the pressure difference between the inlet and outlet. Delta P would be plotted, so the pressure drop, as a function of Reynolds number and again the angular width 2 alpha. Increased pressure drop for narrower channels and higher Reynolds numbers are to be expected. Lastly, we have streamlines. This is the flow pattern visualized by streamlines showing how fluid particles move within the channel. This would be a great contour plot of the stream function. And that's the end of my presentation on the Jeffery-Hamel flow. Please let me know if you have any questions. Thank you so much. Bye.